From the previous video, you should have understood that the coefficients in front of each one of these molecules is the relationship. So this says you have 1 mole of carbon monoxide for every 2 moles of hydrogen for every 1 mole of methanol. Those are not mass relationships. They are molar relationships. Why? Well, if you recall, we multiplied each one of those coefficients by Avogadro's number. That's how we got the mole. So instead of 1 molecule, it was 1 mole of each substance. Here's another equation for the synthesis of water. Those are molar relationships. It says for every 2 moles, we need 1 mole of oxygen to make 2 moles of water. However, the law of conservation of mass says if we have 4 grams and we add to it 32 grams, in a perfect world, we should end up with 36 grams. Because if you recall, matter is neither created or destroyed, only changed, conserved, rearranged. Your book has some awesome definitions on how to do this. They're very wordy, but it has step-by-step directions. You can do this, but essentially we're going to go from grams of A to moles of A, to moles of B, to grams of B. Or shortly, grams to moles, moles to moles, moles to grams. So you're going to start off with grams of A, and using the molar mass, you're going to go from moles to A. Now, if you recall, the molar mass has the units of grams per mole. So I'm going to go ahead and add that in there as soon as I can find my pen. There we go. Grams to moles. That'll allow us to convert. Once we have moles of A, then we can use the molar ratio from the balanced chemical equation. So I'm going to put that in there. Where's my pen again? There it is. The balanced, remember it has to be balanced, chemical equation. Once you have moles of B, then once again, you can use the molar mass to get back to grams of B. That's all there is to these problems. Assuming you've already read through this problem, a good first step to do is to make a plan. Now, I like to make a plan by always first writing the balanced chemical equation on your paper. So that's pretty much the first step. You got to make a plan. Well, no, I didn't say that. Balance the equation. Assuming the equation's balanced, then you can make a plan. This part's really important. I know I keep saying it, but it's really important. So I like to write 3.5 grams under what I have. And then I'm going to put what I'm solving for there. So the problem's really saying, how much iodine do I need to make all that aluminum go away? I want all the aluminum gone. So if I have grams of aluminum here, I need to convert that to moles of aluminum, because that's the only way I'm going to get from moles of one substance to another. Once I have moles of that, then I can solve for grams. Now, another way to make the plan is to write it like this. I've seen both ways done. Works just fine. Just make the plan. So once you have your plan made, and I'm going to go ahead and rewrite it here so we have 3 point, I'm going to go ahead and put 50 grams since that's what the sig figs are. And I need grams of this to make all the aluminum go away. So moles of this to moles of this to grams of that. Or you could have done it like this. Either one's fine. Just make the plan. Now you're ready for dimensional analysis. So we're going to start off with what's given, which is 3.50 grams of aluminum. And remember, if this unit's here, you got to chase that unit down. So grams of aluminum, and according to the plan, you're going to go from grams of aluminum to moles of aluminum. Where do you find that conversion from grams to moles? Well, off the periodic table, of course, the molar mass. So it's 26.98 grams of aluminum for 1 mole. Remember, molar mass is always going to be per 1 mole. Well, that gets our grams of aluminum to cancel out. Now we're ready to try to see, is moles what we want for our final answer? Nope. So we need to chase this unit down to moles of aluminum. And according to the plan, we're going to go from moles of aluminum to moles of iodine. Where do we find those numbers? Well, the balanced equation. So we end up with 2 moles of aluminum, because there's a 2 right there, and 3 moles of iodine, because there's a 3 right there. Well, that means our moles of aluminum just canceled out. Is moles of iodine what you're after? No, so we have to do one more step. So we're going to do moles of iodine, to grams of iodine. And where do we find that conversion from moles of iodine to grams of iodine? Well, back to the molar mass off the periodic table. So off the molar mass, we know it's 126.90 grams of iodine for every 1 mole. Well, let's see. That went ahead and made the moles of iodine cancel. Now you're ready to punch all this into your handy-dandy calculator. Made my line too long. So what's this going to equal? Well, let's take a look. So we end up with 24.69 grams of aluminum. Now let's check our sig figs. This one has 3 sig figs, so 24.7 grams of aluminum. So what this problem is saying, if we need to make all 3.5 grams of aluminum disappear, you're going to need to have on hand 24.7 grams of aluminum. And we're done with the problem. Okay, assuming you've read through this problem, I want to get rid of all that word stuff and just leave myself with the balanced chemical equation. Now, the problem said, if we have 10 grams of sodium hydroxide, yeah, that's a 0. 10 grams of sodium hydroxide, how many grams of this do we need to make all of that go away? And the original number was 10.0, just so we remember our sig figs. So make a plan. So for every 10 grams of sodium hydroxide, we need to go to moles. That'll allow us to get to moles of carbon dioxide so we can get to grams. So let's do the problem, dimensional analysis. Oh, is the equation balanced? Yeah, that looks good. Good. So here we go. We have 10 grams of sodium hydroxide. And I'm trying to draw a straight line. This is harder than you think. Okay, good. So grams of sodium hydroxide go down here. And according to the plan, we want to go from grams to moles. Where do you find that conversion? The periodic table. Okay, so go find the molar mass of sodium hydroxide. Go ahead and pause the video, really, so you can do it. Anyway, I like to use 39.998 because I'm a little retentive that way. If you used 40, I don't think it's going to make a huge difference. Well, that just made grams of sodium hydroxide go away. Don't forget to put the chemical there, because moles of sodium hydroxide go down here, and I see it all the time. Students get lazy, they start dropping the chemicals, and they make mistakes. The plan says go from moles of sodium hydroxide to moles of carbon dioxide, so moles of CO2. And according to the equation, we have 2 moles for every 1 mole. Oh, I didn't make my line big enough. All right, moles of that. All right, we have moles, we need to get to grams. So 1 mole of carbon dioxide has 44.01 grams of carbon dioxide. All right, now we just need to use the handy-dandy calculator and punch it in. So we end up with 5.50 grams of CO2. So in order to make all of the 10 grams of sodium hydroxide disappear, use up, we're going to need to use 5.50 grams of carbon dioxide. And as there were 3 sig figs in our original number, I had to use 3 sig figs there. And we're done. Try this problem on your own. See what you can do with it. The problem says if we have 10 to the 3rd grams of lithium hydroxide, how much carbon dioxide can that absorb? Well, we're going to have to go from grams to moles, moles to moles, and moles to grams. Try the problem now if you haven't already. So 1.00 times 10 to the 3rd grams of lithium hydroxide. attempting to draw a straightish line. Grams is up here. We got to bring that down here. And the plan says you're going to go from grams to moles. And the periodic table is always going to be 1 mole of lithium hydroxide to go calculate the molar mass. All right, so 23.95 grams of lithium hydroxide. That made grams of lithium hydroxide cancel. And the plan says go from moles of lithium hydroxide to moles of carbon dioxide. So 2 moles of lithium hydroxide for every 1 mole of CO2. All right, that made that cancel. And now we need to go from moles of CO2 to grams of CO2. So 1 mole of CO2 for 44.01 grams of CO2. Mind you, it's always grams per 1 mole. Always. Our final answer then, using the correct number of sig figs, is 919 grams of CO2. So 3 sig figs there. This means 3 sig figs there. Let's see, better, 1,000 grams of lithium hydroxide can absorb 919 grams of carbon dioxide. See what you can do with this problem. Go ahead and pause the video and see how you do. Okay, well, let's make a plan. 3.50 times 10 to the second grams. I'm not sure why it was written that way. To moles. Now we need to go to moles so we can go to grams. Starting with the 3.50 times 10 to the second grams. I guess I could have just written 350. SOCl2. Okay. Straight line. Not bad. Okay, grams to moles. And since it's grams to moles, it's always going to be 1 mole. Now I got to go find the molar mass. That gives us 118.91 grams. Grams canceled. We don't want moles, so we have to convert from moles of this to moles of water. So 1 mole SOCl2 to 1 mole of H2O. And those cancel. Now we need to go from moles of water to grams of water. So 1 mole of water has 18.02 grams of water. Now we're just ready to finish the problem. Final answer then is 53.0 grams of water. And as there were 3 sig figs here, we needed to have 3 sig figs in our final answer. Using the same balanced equation and the same starting reactant, so we have 3.50 times 10 to the second grams of this. How much how much hydrogen chloride is going to be produced? So we're going to go from this to moles, all the way over to moles of this, to grams of this. Okay, so 3.50 times 10 to the second. And again, I could have just written 350. Don't know why I didn't. Okay, straight line's harder to draw right there for some reason. And from the previous problem, if you recall, we have the molar mass is 118.91. It's much harder to write on the board down here. Sorry to complain. All right, that made those cancel. And according to the balanced equation, we have 1 mole of SOCl2 for 2 moles of HCl. And those cancel. And 1 mole of HCl has how many grams of HCl? So that gives us 36.46 grams. Here we go. Let's finish it up. So we end up with 215 grams of hydrogen chloride, I guess. So in order to, if we are going to use up all 350 grams, we're going to end up making 215 grams of hydrogen chloride. Up next, we're going to talk about limiting reactants. Yay!